Okay, so here we've got another example, and we'll do the same sort of breakdown here. So this transformation is referred to as the reflection about the origin, specifically in R2. So we've given it a name, it's called T. Let's just add this arrow to indicate that that's the action that T performs. Okay, so let's look at our domain here. We've got the standard basis vectors, E1 and E2. Let's just sketch a picture of them. So we've got E1 is equal to 1, 0, and then we've got E2 is equal to 0, 1 over there. Okay, and as usual, this determines a square called the unit square, and you can see what is this reflection doing to the unit square. Let's see if we can kind of see. So here's the unit square, and it's reflecting it down into a different quadrant, right? But it's doing it actually in a very specific way. To see really exactly what's happening and to make sure the orientation is right, notice they've got the tail and the head have gone to very specific locations, right? So this is not just any reflection. This is a very specific reflection. The best way to think about this, I think, is to think about it this way. First, you can take the square and reflect it across the vertical axis and take the mirror image over here, and then flip it down across the horizontal axis and take the mirror image down here. And that will get you essentially the action that this transformation T has performed. Okay, so what I mean by that, the important thing to notice is that you're not like this corner up here. This did not get sent to this corner down here, right? Because here you have the head of the fish. I'll just draw the googly eye there. But if you look over here, that's not what you see. You actually see the tail of the fish. So it didn't simply get reflected like this this corner to this corner and this corner to this corner. That would be a different reflection, but that's not what's happened, right? So they've clarified that with these arrows here. So the head is going down to this side and the tail is going over to this side. But you should stop and convince yourself that the first thing I said, I think I undid one too many actions here. There we go. You should convince yourself, stop and think about it for a second. You should convince yourself that this is the same thing you would get if you took the fish and reflected it over here and then reflected it vertically. That would get you the same thing. Okay, so let's take a look. What did T do to each of the standard basis vectors? Well, it took E1, this one here, and it brought it over here. So now you've got T of E1 over here, right? So this is T of E1. And then T of E2 got flipped down so that it's pointing downward, so that you've got T of E2 right here. This is T of E2. Okay, and once you understand what T does to the standard basis vectors, then you have the standard matrix. And once you have the standard matrix, then you understand exactly what the transformation is doing. So we're ready to do part A here. So for part A, I'll just start here. So for part A, our standard matrix is going to be given by the matrix whose columns are just the outputs from the transformation T when you plug in the standard basis vectors. So T of E1 was negative 1, 0, and T of E2 is 0, negative 1, and that's your standard matrix. Okay, part B is there's a mistake here, isn't there? Is P 1 to 1? And then it says is P onto. Let me change these. What you really want to ask is T 1 to 1, and is T onto? Because the name of our transformation here is T, not P, like the previous question. Okay, so for part B, we want to know, is T 1 to 1? So in other words, if you got two different vectors, are they guaranteed to be mapped to two different output vectors? And, well, in a sense, no information. Here's a rule of thumb, good rule of thumb you could use. Was any data lost, would you say? Was any information from this picture lost when it was passed through this transformation and reflected down here? And the answer is no. The image is completely recoverable, right? All the bits of information are still there. They're just disoriented and they're just moved around. But you could certainly just flip the picture back and recover all of the information that you had. So you didn't throw any information away. That's another way of thinking about one-to-one, the property of a transformation being one-to-one. And if you had, here's another way to think about it. If I were to just to draw any two specific points, and they could be, doesn't have, oops, it doesn't have to be those specific points. It could be these two, or it could be these two. It um, could be those two. Could be, oop, I went too far there. It could be those two. There's nothing specific about these points, right? Let's go with these two though, because they're in the simpler quadrant to think about. If you take these 2 points, for example, is there any risk that they're going to get sent to the same output vector? And the answer is no. If you reflect them about the origin, and the way to see how to do that would be just to draw a line directly to the origin, and then draw another copy of that same line segment, and that would put you right about here. Let's say I'm going to remove this from the picture afterwards because it's just going to get too cluttered otherwise. That sends it down here. What does it do to the other point? Well, if I draw a line segment there, and then I can actually copy and paste here. Copy this line segment and then draw another copy over here. Then I can say, okay, that it's going to send that point over here. Okay, and those are certainly different points. And what you'll quickly convince yourself of, as long as these 2 points are not the same, they're going to have some positive distance between them, right? By positive distance, I just mean if you measured the distance between those 2 points, it's going to be positive. Well, these 2 points are going to have the same distance between them, or it certainly looks that way geometrically, right? And so the idea is, as long as the 2 points you start with are different, the 2 points that they get sent to are going to be different as well. And this is not a proof, right? I just drew 2 points and drew some arrows. That's not rigorous, convincing proof, but I think it's at least gives you an idea of why you ought to expect that in this case the answer is going to be yes, that t is going to be 1-to-1. Okay, maybe I'll. Oh, what's going on? It's locking up here. Okay, that seems to be better. So maybe I will leave those on there. There's no reason to. Let's add some explanation here. So let's say this is x. Call this x and y. We certainly have x not equal to y. And down here, you'd have t of y, and down here you have t of x. And we certainly have t of x is not equal to t of y. It's kind of getting a bit too close, so I'll just move it over a bit. So in that case, with those 2 points, it seems like it worked, right? We had 2 different points, and t mapped them both to different output vectors. And I hope you're convinced that if I were to move these points around at all, I'd move these ones around as well, but they'd still be different. As long as these are different, these 2 points are going to be different as well. I hope you're at least convinced now. But how do we prove this? How do we write this as a mathematical statement and make it convincing? Well, what we're going to do is we're just going to assume that we've got what would it look like if these were the same? We're going to do this. We're going to prove that if these 2 points are the same, the only way that can happen is if these 2 points are the same. And if we can prove that, then that's enough to say that t is 1-to-1. So let's assume that we have 2 points, x and y. Let's write them as vectors. So x is going to be as x1, x2, and y is going to be y1, y2. So we've got 2 vectors in R2 with the property that t of x is equal to t of y. We're going to show that automatically means that x and y have to be the same picture. So, okay, or the same vector. So how will we do that? Well, if t of x is equal to t of y, then we can say the following. Well, what is t of x? Well, it's the standard matrix A multiplied by the vector x, which is x1, x2. And that's got to equal to t of y, which is going to be the standard matrix A multiplied by the vector y, which is y1, y2. And now let's actually just perform the matrix multiplication. So you're going to get x1 multiplied by -1, 0, plus x2 multiplied by 0, -1. And on the right-hand side, you'll have y1 multiplied by -1, 0, plus y2 multiplied by 0, -1. And you can kind of see what's happening here. I mean, the left and right-hand side so far are still just completely identical. The only difference is we have x1 on the left-hand side and y1 on the right-hand side, and then x2 on the left-hand side and y2 on the right-hand side. But the structure of the expressions are identical. Why is this stuck again? Okay, there we go. Something's wrong with my screen. Anyways, okay, well, let's keep going. So we'll have, this is going to give us negative x1, 0, plus 0, negative x2 on the left-hand side. And on the right-hand side, we'll have negative y1, 0, plus 0, negative 1, probably negative y2. And what we're building towards now, if I finally add these together, I'm going to get negative x1, negative x2 is equal to negative y1, negative y2. So now we've got an equation involving two vectors, two two-dimensional vectors. But two two-dimensional vectors are going to be equal exactly when their corresponding coordinates are equal. So negative x1 and negative y1 have to be the same thing. So negative x1 is equal to negative y1, and negative x2 has to equal negative y2 in order for the second coordinates to be the same, right? So what does that tell you? I'm going to change that to a better drawn 2 here. So that tells you that x1 has to be equal to y1. Just get rid of the negatives, right? x2 has to equal y2. So that's enough. Because look at what was x1, y1, and x2, y2. They were the coordinates of the vectors x and y. So if x1 and y1 are the same, that means the first coordinates of x and y are the same. If x2 is equal to y2, well, then the second coordinates of x and y are the same. So therefore, you can say that, therefore, the vector x is equal to y. So we did it. That's what we wanted to do. We assumed that we had two input vectors that mapped to the same output vector, and we were able to prove from there that the only way that can happen is if the two input vectors were actually the same, just with a different label. So we can say t is 1 to 1.